Okay, hello everyone and welcome to the International Grouting Webinar Series. My name is Kathleen Bensko. I am the co-chair of the DFI International Grouting Committee with Rafaela Granata. And we have three very exciting presentations to give to you today. And hopefully that you will enjoy it. And could we go to the next slide, please? Okay, during the webinar, all attendees will be muted. Question and answers will be followed. At the very end of the presentation, we'll just run from one presentation to the other. And if you do have questions, please ask the question in the chat box, and we will get to all of them at the very end. Afterwards, the PDA certificates will be available after paid registrants complete the webinar evaluation through the event module. Access instructions will follow via the email whenever you log in and do that. Register at www.dfi.org for the other webinars, which is the DFI website, and please give us your feedback and suggestions. Any questions that we don't get to or we're unable to cover at the end, please direct your questions to events@dfi.org, and we will respond accordingly and get your answers back to you. So our speakers today will be Andreu Ferrero, David Miller, and Nancy A. Straub. Our first speaker will be Andreu. His presentation will be permeation grouting using polyurethane and acrylate resins in a silty sand, injection methods, in-situ verification testing methods, and laboratory results. Andreu Ferrero is a North American technical manager for NEEF, GCP Applied Technologies, a Saint-Gobain company. Ferrero is a licensed civil engineer in multiple U.S. states and serves on the DFI International Grouting Committee. He is an active member of ASCE also. During his career, Ferrero has worked on many large-scale deep foundation projects, public works projects, and provides grouting consultation services to many of the largest contractors in North America. During his early career, Ferrero worked on drilling rigs conducting geotechnical, mineral, and water exploration before pursuing his education in his mid-20s. Ferrero received his bachelor's and master's degree in civil engineering with a focus on structural and geotechnical engineering from Portland State University in his home state of Oregon. Our second speaker will be David Miller from ADM Consulting. His presentation will be navigating the spec dealing with difficult soil mixing specifications. David Miller, PE of ADM Consulting, is currently the chair of DFI's Soil Mixing Committee. He has 36 years of experience in ground improvement techniques, especially deep soil mixing. He has completed projects in the US, Canada, Australia, and New Zealand. He worked on the first multi-auger project in the US at the Jackson Lake Dam, one of the first large diameter, 12-foot, soil mixing applications. He has led fast-tracked applications for emergency post-Hurricane Katrina, multiple DSM cutoff walls up to 135 feet deep on levees, DSM for seal slab for railroad grade separation, treatment of dams for liquefaction prevention, wharf repair following the 2011 earthquake in Christchurch, New Zealand, and excavation support of groundwater cutoff for major high-rise construction. He was the project director for 3 USACE task orders, totaling 16 miles of soil mix cutoff wall. Mr. Miller has a bachelor's degree from the University of Texas and is a registered professional engineer in Texas. He has published several papers on the use, specification, and quality of soil mixing, along with case studies. Miller has previously served as executive director, geotechnical operations for Forgen, project director for Bauer Foundations, and senior vice presidents for Rato. Nancy A. Straub from GEI Consultants will present Unintended Consequences, How Improving the Turf on the National Mall Became an Inauguration Crisis. Nancy Straub is a senior geotechnical engineer at GEI Consultants, Inc., and in their Rockville, Maryland office. She also serves as the branch manager for GEI's Washington, D.C., Maryland, and Virginia offices. In addition to being a professional engineer, she is a lead AP and an Envision SP and a verifier. Ms. Straub has over 28 years of experience in geotechnical, environmental, and sustainability engineering in the Mid-Atlantic area, as well as across the U.S. and around the world. She has worked on a wide range of geotechnical projects, but her passion lies with forensics, problem soils, and rock mechanics. She is a member of DFI's Sustainability Committee, the Institute for Sustainable Infrastructure, and the Society of American Military Engineers. She received her bachelor's degree in civil and environmental engineering from the University of Pittsburgh in Pittsburgh, PA, and her master's degree in civil and environmental engineering from the University of Maryland in College Park, Maryland. So with this, I'd like to turn everything over to Andreu for his first presentation. Please sit back and enjoy our presentations. Thank you for attending.
Hello, my name is Andreu Ferrero, and we will be going over a presentation on permeation grouting. I live in Portland, Oregon. I'm the Technical Services Manager for NEEF North America. Kathy introduced me, so I won't linger there for too long. Thank you, Kathy, and the rest of the DFI team for hosting us. So, okay, yep. So the use of polymer grouts in the earthwork industry is relatively new. There is limited data that shows the actual performance in situ. So we conducted a demonstration in Vancouver, Canada in 2020, January of 2020, where we filled a large construction dumpster with local silty sand, and then we injected that compacted and moisture-treated sand with a polyurethane resin and an acrylate resin. The intention here was to monitor the grout take, monitoring the volume of grout injected per unit volume of soil treated, monitoring the polymer expansion within the soil that we were injecting into, monitoring the pumping rates and pressures so we could determine the permeation versus fracture pressure in the soil, in this type of soil. We also looked at the composite soil resin properties. We did dynamic cone pentrometer testing in situ, and then we took some core samples of the treated materials, and we conducted triaxial, direct simple shear, and unconfined compressive strength testing. So this is a gradation curve for the sand that was used. So this was from a quarry in the Vancouver area that is used for construction. As you can see, the silty sand had about a 12.1% fines content. So it was right there in kind of the mid-range of what we would expect to be groutable. Generally, things above 20% fines content are not going to be very groutable. So this was a good example of a slightly dirtier soil that we wanted to use to see what the results would be. So the materials we used were the NEEF Cut Pure, which is a single component hydroactive polyurethane. It expands up to 30 times its original volume. It has a variable reaction time depending on the type and amount of catalyst that you use. And it has about 180 centipoise viscosity. And that is the first picture on the left with the green cup. So that material reacts when it comes into contact with water, and then it expands. As you can see in the photo, it expands upward in a rigid body. And then once it's done expanding, it becomes hard and is not flexible. And it provides a barrier to water ingress, and it also stabilizes soil. The NEEF AC400 is an acrylate gel, the picture on the right. There is no expansion in this product. It has a variable reaction time depending on how much and what type of catalyst is used. has a viscosity around 3 to 6 centipoise. So it's going to be much lower viscosity than the polyurethane. It's going to be able to penetrate tighter soils and tighter defects. So the injection layout is as shown on the screen. We did a test injection on one side of the container, and then we did a polyurethane treatment zone and an acrylate treatment zone as shown in the layout here. The gate of the container was along the treated side with the intention of showcasing the stand-up capacity of these materials. This is the injection layout. The probes were installed, and the soil was compacted around the probes. Probes were marked at 1 foot intervals, and to create even lift heights for injection. This is the injection lift sequence. So we drive the probes down to within about 6 inches of the bottom, and then we inject the first lift, followed by the second lift, the third lift, and the fourth lift, making sure that we leave at least a couple of feet of overburden with an additional overburden pressure of some sandbags to prevent any kind of heaving or chimneying of the material up around the grout probe itself. The intention here is to create a grid that these grout columns stacked up on top of each other will interlace and create a solid treatment area. These are laboratory results from similar types of open-ended injections. So you can see on the left is a single lift grout ball, and on the right is a double 2 lifts. So the first grout mass on the bottom stays relatively spherical, and then the second one kind of mushrooms over the top of that one, expanding the diameter a little bit. This is a typical injection assembly. From the pump, the material flows to the ball valve, which acts as our on-off switch. The needle valve is what we use to control the flow rate or pressure into the system. And then the pressure gauge is what we use to monitor the back pressure on the system. So once we open those systems up, we'll have grout flowing into the soil, and then that pushes back on the pressure gauge, telling us what pressures we're exerting on that soil. These are quality control and reaction times for each each batch that was mixed. This is the acrylate grout, and you can see there that the reaction times are generally right there around 1 minute and 30 seconds to 2 minutes. And that is in a cup test. So when these materials are injected into the soils, that reaction time will be delayed because these reactions are exothermic. The catalysts generate heat within the materials, which creates the reaction. So in the soil absorbs some of that heat, so it takes a little bit longer for that material to react. With about on average, a 1 minute and 45-second cup test reaction time, you're going to get about a 5.5 to 6 minute reaction time in the soil, which extends the amount of permeation you can do and makes that permeation sphere bigger the longer the set time is. So we targeted an injection pressure of 5 to 15 psi, so as not to fracture the soil. This is an image of one of the contractors that was assisting us with the injection. This is a pressure and flow comparison for the cut pure polyurethane. So as you can see, the flow rate changes slightly with an increase in pressure. As we increase that injection pressure, we are getting a slight increase in our flow rate. And that makes sense because the material is about 180 centipoise viscosity. So it's not really thick, but it's relatively thick compared to water. So as we increase that injection pressure, we do see an increase in flow rate, but it's not exactly linear. You got to increase that pressure a little bit higher to just start slightly increasing that flow rate up to a certain point where that injection pressure goes up to a fracture point, where then you fracture the soil with the pressure from the grout, and then your flow rate will greatly increase, because now you have an open path for that grout to flow. And that's what we're trying to avoid in permeation grouting, is that fracture pressure. The AC400, which is the low viscosity acrylate, around 3 to 6 centipoise, did not see a change in flow rate with the injection pressure changes. Actually, we couldn't get a pressure resistance on the pressure gauge because the material that we were injecting was so low viscosity. It was just flowing through that silty sand and not back pressuring up. So we were able to increase that flow rate, but we didn't see any changes in the pressure. This is the trial injection for the polyurethane that we injected. As you can see, it's kind of an oblong, oddly shaped structure. We injected 24.25 liters of material of the polyurethane, and then we measured approximately 130 liters treated soil, which gives us about a 5.3x treatment volume. Now, if you back calculate out the soil volume from that volume, you can see that you get about a 2.5x expansion of the polyurethane within the soil, which is greatly different than the 30x expansion potential that the polyurethane has in free rise or in a cup test. So what that tells us is that the material in the soil is going to be much, much denser than the material in the cup test. So, and we see that here, this material here is has a consistency of weathered sandstone, fairly tough. You can hit it with a hammer a couple times before it'll fracture and break. And then the sand doesn't ravel off as you're touching it. So the dimensions of this guy, about 7 feet long across the base, and about 5 feet tall. And then on average, it was about 11 to 14 inches in width there. So we did a series of dynamic cone pentrometer testing on the treated and untreated soils. DCP testing is used to determine California bearing ratios and verify standard penetration test values. These are the results from the DCPT testing. As you can see, the orange squares are the untreated soil. The blue triangles are the polyurethane treated soil, and then the blue X's are the acrylate treated soil. Now, the polyurethane treated soil doubled the penetration resistance over the untreated soil. And the acrylate treated soil didn't have really any change in penetration resistance from the untreated soil. Now, the acrylate material reacts and forms a gel, so we don't really expect that to increase the penetration resistance, but it will add cohesion to the soil, which will increase the stand-up capacity of that soil. California bearing ratio is generally used to evaluate road subgrade and is expressed as a percentage. I used a correlation from Webster to estimate the CBR percentage from the penetration rate, which shows that we got a substantial increase in our CBR over the untreated soil. Same thing for the SBTN average values. I used a correlation from Ishai in 1988 to correlate the penetration resistance values, or the DPI values to SPTN values. And here again, we see a significant increase in the SPTN value over for the polyurethane treated soil over the untreated soil. And then we did the bearing capacity estimation using the Portland Cement Association value. And again, saw a significant increase, almost doubling the bearing capacity for the polyurethane treated soil over the untreated soil. We also did track seal testing. You can see the sample on the left has a nice classic shear plane. And we can see that the Unconfined compressive strength is pretty even across the board, but we do have a correlation between stress and density. The higher density of the material, the higher stress that it would be able to take, which is pretty standard for this kind of material. Looking at the shear strengths of the untreated versus the treated soil, we took the direct simple shear values of shear strength for the untreated soil and compared that to the unconfined compressive strength shear values for the treated soil and the triaxial testing values for the treated soil. And we see that the UCS and the CIU triaxial test give us about the same shear strengths, which is nearly a little more than double the untreated soil in the direct simple shear. Conducted a Moore circle analysis on the treated soil and found a value of about 870 kPa cohesion. That silty part of the sand does add a little bit of cohesion to the sand itself, but we were postulating that the majority of the cohesion is from the polyurethane treatment and what we're calling a cementation cohesion value. So for discussion, the main points are that the polyurethane grout can treat up to 5 times its liquid volume when permeated into silty sand in shallow unsaturated conditions. Some soil fracturing did occur, forming thin veins of pure reacted grout throughout sections of the grout mass. Permeation appeared to emanate outward from these veins. A diamond grid injection pattern created a relatively uniform soil grout composite block and the elevations injected. Typically, we found that it was around 90 to 95% coverage rate with some edges and corners not getting fully covered. The soil grout composite exhibited a much higher DCP resistance than the compacted soil alone, 33% higher SPTN correlation, 133% higher CBR correlation, and 80% higher bearing capacity estimates. The acrylate grout provided enough stability to support a 4-foot cut in the soil and was easily excavatable. As we discussed, we didn't expect the acrylate to increase the penetration resistance, but we do see the value in supportive excavation for shallow trenches and excavations. This is a product that's used in underpinning, for example, to stabilize soils while contractors are excavating underneath footings so that the soil around them doesn't collapse in on them. It was shown that the increasing flow rate of the polyurethane injection increases the back pressure, causing soil fracture above approximately 1.5 bar for shallow injections. And then quite the opposite with the acrylate, increasing the flow rate had no effect on back pressure. And we theorize that that's because the viscosity of the acrylate is just so low that it wasn't creating any kind of pressure resistance within the soil itself. We did a lot of laboratory testing, which was verified with our in-situ testing results. The shear strength of the polyurethane treated soil was pretty spot on with the in-situ testing and the laboratory testing, as was the unconfined compressive strength and the cohesion of the soil increase. And here is an image of that 4-foot high, a little more than 4-foot high gate open with the material treated there. And you can see me down there in the bottom left trying to measure some stuff. So thank you for joining us. I'd like to open up for any questions. Oh, I see you down in the chat there. Probably some questions. Oh, yep. Great. Thank you very much.
Good morning, everyone. I want to thank you for joining us. My name is Dave Miller with ADM Consulting. I'm presenting a little bit different take. It's not really a case study, but it's examples of issues that you have when the specs get difficult for soil mixing and ways to work through those in a cooperative effort with the client. I want to make it clear that these are only thoughts and opinions. You can't go to a client and say, well, Dave Miller said it was okay. But so nothing's set in stone. They're all suggestions and offers, and we're just trying to give you ideas on how to professionally manage issues when they arise. So soil mixing specifications are critical to ensuring the successful execution of a soil mixing project. Without them, you're just going out and mixing soil and not really giving the client any real understanding of what he's getting. You're not addressing any quality control issues and things like that. So there's a lot of unclear language during this time, and that creates lapses of confidence. So that you need to work closely with the client to make sure that there's an understanding of what's happening. You want to be sure you're assessing the quality, and I'm going to try to give you some effective strategies to address some of these challenges. The collaboration with amongst stakeholders, seeking clarification from the project owner and designer is pretty paramount to a successful project. Okay, so there's several different types of soil mixing equipment. We're predominantly looking at the, sorry, this is very touchy, at the deeper technologies. For instance, a multi-auger piece of machinery that has 3 to 6 augers. Actually, they all overlap with each other, and they kind of blend in a pug mill fashion. To there's even single augers that are used for more mass stabilization, things like that. The multi augers typically do a wall or a grid application. Diameters up to 5 feet, but 3 foot is more common. Most of the multi auger machines are proprietary, although there's some hydraulic machines that are on the market that don't go quite as deep, and so there's competition coming to those. The single auger is more for bearing, mass treatment. I've seen diameters up to 12 feet. 6 to 8 foot is more common. All right, the next one is the cutter soil mixing. It's the most readily available one is made by Bauer. It's commercially available. And on the right base machine, it can achieve significant depths of, up to about 140, 145 feet, installing panels of soil mix columns or soil mix elements. All right, then lately there's the advent of some of the trenching technology. Um, so there's some manufacturer out there that has some very large homegrown machines. They're all proprietary. They make them themselves. They can go quite deep. Um, but now you're starting to see commercially available trenching machines that are good for attachments, and those are generally good to depths of about 40 feet. But they're growing. Some of the challenges with the soil mixing is assessing the effectiveness of the soil improvement, continuity of it, evaluating the depth of penetration into the specified competent material, availability of sufficient geotechnical data that covers the extent of soil treatment, and the difficulty in predicting the rheological properties of the soil binder mixture. So those are all issues that we're trying to address. Okay, so there's a working group that's formed through DFI and the USACE to work through some of these specs with the Corps to address some of the challenging issues. And the things we're trying to address with them is subcontractor involvement, assessing verticality, dealing with low strength material, because soil cement really is kind of a low strength. We're talking usually 2 to 400 psi, and that's difficult to test and obtain samples for and things like that. Measurement wide drilling, which I think is a very important advent in the technology, the data acquisition and permeability. There's several people working on this. I can't name them all, but certainly thanks to Mary Ellen and Michael Arnold, Eric James, April Fontaine, Li Xing Xiao, Mike Sicola, Mark Stanley, and many others. The group has taken a break for the summer, and also since the Corps is in a little bit of a state of flux. So here's a photo of us all in our last meeting back in October. The interesting thing is when you get the parties involved, when they're not trying to defend a position on a particular project, they're very open about listening to ideas to change the spec. We also get an opportunity to understand what their issues are when they write the spec, or what their handcuffs are with this. So they've been very productive meetings, and we hope to continue them. All right, so contractor involvement. This is especially critical if you're a subcontractor. Typically, the owner and the subcontractor have no direct contractual relationship, and that can create problems on a project, especially as technical as the soil mixing. So you want to try to be sure you're involved with the technical aspects of the meetings and things that are discussing you. You don't want to be sure you want to be sure there's no lost translation. So when it's critical, it's important to be on technical discussions and planning for the work. This can reduce the eliminate claims and delays. As everybody works together, you create a trust, a better reaction when problems arise. You leads to more productive meetings. Uh, After owners specify experience in soil mixing, often they specify experience in soil mixing personnel. It's beneficial to have their thoughts. So if they want certain people to be involved in the project, they should be involved in those meetings. You don't have to worry about a loss of translation from the GC. And you get a thorough understanding of each party's issues, and leads to better engineering judgment. Okay. In most circles, that's called common sense, but you get paid more if you call it engineering judgment. But it's certainly critical that everybody understands what the other issues are for everyone. Okay, so the property is soil cement. So first of all, you want to create a mix design. And you do this by knowing the soil types, the moisture, stiffness, things like that. And then you want to know how much mixing energy, how much effort that goes into that mixing. Now, there's in the industry, they've established what's called a blade rotation number, and that's essentially the numbers that a blade passes through the soil, so that you get an idea of how much mixing is in that. Some people call it an energy index. Some people call it, just rotations, but it's all monitored to judge how much energy goes into that to evaluate the effectiveness of the mixing. Okay, so mix design development. This are the steps that you need to take in order to put together a good project. You want to be sure you do a mix design. It's pretty paramount for a project to have a mix design, so you can get an idea of how the soils will react to the binder, how much binder to put in, what kind of moisture contents to have. Certainly more cohesive soils will have a more difficulty blending. And you want to prepare that mix. Then you go on and install it. And then after that, obviously, you test it through verification sampling. So for the development of that, you want to analyze the specifications and honestly know what they're looking for. Based on your previous knowledge and analysis of the available geotechnical information, develop several design mixes. Then you produce these design mixes using the soil and water samples from the job site. Then you pick the appropriate design mixes to test on site, and then test them on site and move forward with production after that. After that, you go into some verification sampling. Anyway, so there's wet grab sampling to make specifications. You test permeability, typically at 28 days. Most specs are written around an unconfined compression test at 28 days. And then a lot of specs require you to core it. Sometimes that's not really practical depending on the stratigraphy. And then the backup option in my mind is televideo and a geologging. Sometimes it's required. And then if you have a permeability test, so you look at ways to test that. Many times they specify in-situ tests like falling head or pump tests. Other times they can do it from wet grab samples. So here's a shot of the difference in coring and wet grab sampling. Coring uses the conventional coring to achieve samples after you've achieved a sufficient strength, and but obviously prior to the testing date. You can't test a 28-day core if you didn't core it for 35 days. But a lot of projects, because of that difficulty, some of the strengths are older, but the important thing is, are you meeting the strength? Are you meeting the intent of the project? Okay. So cores can be problematic because the material is relatively low strength. It's hard to core. Um, Wet grab samples typically have a sample box mounted to the auger and sent down to retrieve the sample. At shallower depths, you can separate the sampler from the drilling and put it on a beam or something like that. Okay. So the core samples, coring and testing of low strength cutoff materials installed by deep mixing and other methods having targeted unconfined compressive strength of less than 1200 psi can be unreliable. And that's because the matrix is so relatively weak. Okay. So the coring process can damage the cores, and this can lead to misleading results and misunderstandings on the project. But it's also the least intrusive method to drill holes for imaging. And if you get good cores, they can provide an insight of the uniformity of the material. And poor core recovery can be misinterpreted and mean poor wall quality. It can lead to the coring process can lead to microfracturing, rendering the core unusable. Even though it can look great, but the microfractures may not allow it to break. It will create a failure plane along the fracture. And gravels especially are difficult to core because they can break loose and just tear up the matrix completely. Okay, so here's an example of a couple of cores that, this one doesn't look so great. You see a lot of gravels in it, and, maybe not, first impression, it's not well mixed. But if you take a video of that and you look at the side walls of this video, you can see there's a lot of gravel and particles within the sidewall. It's all bound up within the matrix. It's exactly what you want. But the problem is the gravels within the core barrel, they'll break loose and then start grinding up your matrix. So you take this out and look at the core box, and it's everybody panics. They're concerned about the quality of the mixing and things. So a video logger is a good way to kind of counteract that. There's a different core, looks very intact, 100, very good recovery. And if you look at the video for it, it looks very similar to the previous video. So you can see that the coring process can be very detrimental to the observation and the integrity of the wall, or the I guess the opinion on the integrity of the wall. So you want to be sure that you're looking at the body of work and not just one particular item. So wet sampling is one way to achieve samples without the coring. It's quick and dirty. You take the sample right after you've completed the wall while the material is still fluid, and you can put it molded into cylinders, typically 3x6, and you can mold several cylinders, cure them under certain conditions, and then test them at various ages, like 3, 14, 28, and you can even hold some samples for longer strength. The benefits of the wet sample is that's early strength indicator. Like I said, you can test it at 3 or 7 days. You would never be able to core it that soon to test it. It's a non-destructive test. You're not coring into your wall. You're just grabbing a sample while it's still fluid, so the material can close up. All right, and it's one of the better ways to get a sample for permeability testing, in my opinion. So obviously the cons are, depending on the soil, it may retrieve more grout and less unmixed clay lumps. If you have a very cohesive soil and you're getting these lumps, you'll have a tendency for the grout to flow into the sampler easier than the lumps, and that could lead to some results that aren't representative. All right, and that could be misleading. All right, so measurement-wise drilling. I think this is a necessary tool to evaluate the mixing. I think it's it gives you real-time monitoring. It measures various parameters versus depth. But you have to implement a strategy to manage all of the data that comes out. I mean, it's a tremendous amount of data that this technology can put out. Many projects, some of the larger ones, you'll have a separate person just managing that data on a daily basis. So I think that you need to develop a pretty good strategy. It's a lot different from my days in Jackson Hole when I could just count the batches and put one line in for how much cement was used. So it's a very necessary tool to establish that things were done consistently and in a similar manner, and it gives the client a record of what was actually done. So during construction, several drilling variables are monitored in real time: the penetration speed, the rotation, the verticality, slurry injection, depth, sometimes cable load, sometimes crowd, energy index, or blade rotation number, depending on the exact uh, brand that you're using. So here's a schematic of basically what's all monitored and how it's all interconnected to everything. Several monitoring points on the depth, of the volume, the torque or energy being put in, and then that goes back to the operator in the cab. He gets to see much of that data, as well as the operator at the batch plant, so that they're in communication and they're recording this real time data. And then if they need to make an adjustments, they can communicate with each other. Sometimes people forget the slurry is a drilling fluid also, so sometimes you have to adjust your flow rate to help to aid in the drilling process. All right, so here's an example of some of the data that's presented. In this one, it measures the speed, the cable load, which is an idea of how hard they're pressing. As it goes to zero, they've got all the weight of the machine on it. And in this example, I've superimposed a boring, so you can see as it gets into the tougher material at the bottom, the index goes up and the speed drops down. Here's one from Bauer for their CSM. You can see it monitors very similar things, and that's so you can get an idea of what's going on there also. And then there's the SOAMEC, which some of these start to look like video games. There's so much going on in the cab, and but it truly is good information. All of this information can be downloaded onto a drive, or in many instances, it's got a direct communication with the home office, so they can download it and see it. But there's just a lot of data collected on a daily basis, and it's difficult to present that to the client. So my recommendation is the client gets a summary on a daily basis, but all of the detail is submitted at the end of the project. Because literally you could develop hundreds of pages of information on a daily basis, and nobody would be reading that on a daily basis, I don't believe. So this is the SOAMEC system. So again, each drilling company has, well, not each, but many of them have their own systems, but there's also commercially available systems that you can attach to drilling leagues to get much of the same information. All the charts look a little different, but they essentially monitor the same thing. And again, I think this is paramount to the industry and being able to calm clients, and that you've done things on a consistent basis. You can go back and show what your flow rates were, how much was injected, how fast you drilled it, how much energy was applied, things like that. And it's all very important to be able to address issues in the future. Okay. On verticality, it's the specification typically have a verticality requirement for individual elements. They also have a minimum wall thickness, and these often contradict if you look at the total depth versus verticality and how much they can deviate versus the minimum width on what ultimately can happen. So I don't think verticality should be used as an acceptance criteria. It's one of the items that you should monitor, but it shouldn't be part of the acceptance criteria. All right, so instantaneous verticality measurements can be out of tolerance, but minimum thickness and overlap of the wall elements can still be achieved. Um, Alternatively, when vertical limits are met, sometimes the minimum thickness of overlap requirements are not achieved. Um, and it's difficult to measure real time directly on the tooling. Now, there's some non rotating tools that have systems for monitoring the position real time, and manufacturers are working on monitoring the augers real time. But typically, what's relied upon now is the inclination of the mast in both directions and maintaining it within a tolerance. That's pretty much the industry standard. Again, there are companies working on monitoring. There are sensors you can put on the auger, but it's after the fact. You once you come up, you download the data from that sensor and see how vertical you maintain and how out of deviation. And one of the drawbacks to the careful monitoring while drilling is that a client can go back and see, oh, in this section here, you were out of tolerance on verticality. And that can be something as simple, you hit a hard stone and the machine kicked over. But if you read on down through the data, it usually straightens out. And when you come back out of the element, it's straightened out. So it's gotten corrected. But this is one of the drawbacks to the detailed information is you can go back and nitpick a certain spot. I've been in arguments with the Corps about, it kicked over an inch, but if you read through the data and look at it when coming up, it corrected that so that you have a vertical column or vertical element. So this is something that was developed within our working group to kind of demonstrate what I'm talking about here. So you can see on the top, that's the design, the overlap, everything's perfect. You got the minimum thickness. As you go deeper, your deviation is off a little bit, but you're still measured. Your deviation is within tolerance, within spec, and you still got the minimum wall thickness. Here you get up to 120 feet, and your deviation's within spec, but your minimum wall thickness isn't there. So I would suggest the more important detail on this is the continuity and the overlap of the elements, not so much the verticality. It's in nobody's best interest to drill way out of vertical. So everybody's making an effort to drill it vertically. But as you can see here, if the deviation is within tolerance on a deep enough element, your overlap cannot meet that. So the idea should be, maintain the continuity and the overlap. Again, this shouldn't be used for the acceptance, just one of the criteria in the whole bag of information. So permeability, that's one of the toughest things to evaluate and be sure. So you can do in situ tests, and this can lead to poor results. Sometimes the drill hole gets too close to the edge, and then you have some breakthrough, and your permeability is, falsely too fast. You can do rising and falling head tests within those, and then you take that information and run it through an equation. What's the right equation? There's a couple different, and they come up with different answers. So the question is, what is the right equation to use? And obviously, the tests take a while to run. If you have a really good permeability, fairly low, it can take a few days to a week or more to get to steady state to get the actual permeability reading and results. So, and I highly recommend not relying on cores for permeability just because there's so many things that can go wrong with the core, as I mentioned earlier, microfracture, things like that. And cores are good for assessing the mixing and things like that. But overall, I wouldn't rely on cores for permeability. So then you get to, applying the spec contractually. Obviously, if everything goes smooth, you've met all the requirements in the spec, you're done, you bill, you get paid, you get out of there. But it comes down to interpretation many times. So who's interpreting that? And that's where these meetings up front to discuss the issues and where you see that pitfalls might be and things are very important. Always look at what was the intent of the spec. If you're looking for a continuous wall, are your overlaps maintained, or your continuity maintained? Did you retrieve a depth you're looking for? So the contract can turn very adversarial, or it can be more of a partnering situation. And I would suggest that a partnering situation is less difficult on everyone. If you're fighting a claim, everybody's going to get in a defensive mode. And then, are you looking at change orders, or is there a possible VE when you're saying, okay, well, we can't do this, but we can do this, and it'll save you this much money? That's that usually perks up some ears. And it affects your schedule durations and your contract closeout. Okay, and issues will come up, and so it's difficult to rely on just one or two items for acceptance. If there is a doubt over the quality of the entire, use the entire body of the information and review that and make an engineering judgment based on that, and be sure you're at least meeting the intent of the spec. So the benefits of soil mixing is you get a pretty reliable strength gradient as long as you've looked at everything, you get the material in place, you do the mixing energy. You'll find that soil cement can gain strength over a very long time. 28 days is not the end of it, where our concrete curves will flatten out after 28 days. You can see significant strength gains of soil cement on out to a year or more. All right. So it has minimal impact on the environment. The drilling and mixing operation is low noise, low vibration. You can get some lead credits because you're reducing the offall and the amount of materials used. The computerized operation system, it controls everything. It takes the human error out of it, and it's a recordable and defensible thing. It's a very efficient operation. You can easily move it from one spot to the other and do several different areas. All right. So in addition to these, there's schedule savings, limited ground movement, especially if you're adjacent to an existing structure. There's groundwater control for excavation support systems. If you think about it, the lagging's already in place before you ever start excavating, which is kind of a nice situation when you're up against an existing structure or something like that. All right. So, all right. I want to thank you for attending. I want to also thank the companies that help provide. I'm a consultant, so I have to rely on other companies to give me information. And Bauer Foundations, GeoSolutions, Malcolm Drilling, Righto, Trevi, and especially the DFI USS seepage control group that are working together. There's a lot of, they're working very hard to standardize these specs and get things that are workable for everyone. One company I failed to mention was American Drilling. They had that trencher that I showed. So I appreciate it, and I'll turn it over.
Thank you, Dave. My name is Nancy Straub. As I mentioned earlier, I'm a senior geotechnical engineer with GEI Consultants, and I've been asked to talk to you today about a sort of an unusual case history, an unusual project that I worked on a number of years ago that might be appealing to people. So the outline for today's project, I have to give you a little bit of background on the Mall Turf project, which was underway back when this project started. It had some problems in the early days, and the contractor made some repairs. But the problems continued, so there was an investigation. We came up with some hypotheses, developed some remediation strategies, and then ultimately went with a grouting program. So let me give you a little overview. So if you're not familiar with Washington, D.C. and the National Mall, the National Mall is a long linear park in downtown D.C. It extends from the Washington Monument here, which is in the bottom right-hand corner, to the Capitol building on the upper left, which is the east side of the mall. It is a very, very popular and high visibility linear park. And therefore, it gets a lot of traffic. You have a lot of events, you have recreation, you have celebrations, you have demonstrations and protests. Because of this, over the years, the grass on the mall had completely worn away, and the soils had become so overcompacted that the grass could not grow. So as a result, the National Park Service decided they needed to do something about it. This did not look good. So they decided to execute a very comprehensive rehabilitation program. It lasted about 6 years, and it covered the length of the mall from 3rd Street to 14th Street. I'm not going to read all the aspects of the project there to the left, but you can see what they are. But one thing I do want to bring to your particular attention is this one here. Re-engineered the soil to resist compaction and improve drainage. Remember that for later. So the project, the turf project was almost finished by March 2016. They were on their final panel. They were smoothing the grade. They were putting in the granite curbs. They were putting down the turf when suddenly sinkholes started to appear in some locations. So panel 19 is sort of towards the western end of this project. And the initial thought was, hey, all of these sinkholes are kind of near some existing subsurface buried features. So, you know, maybe there's a broken pipe or something and soil's washing in. One of the things that sort of complicated the assessment of what was going on was the fact that the new turf had a plastic mesh in it that allowed the turf to span over sinkholes. So it was hard to see them developing and could create a safety hazard because you could actually walk across this. Kind of felt like walking on a trampoline, but you didn't know how big or deep the hole was below. So in the first few early sinkholes, the contractor excavated them out to try to see what was going on. And in one of them, rather interestingly, they exposed the top of a steel H-pile. It appeared to be cut off about 6 feet below grade. That caused a little confusion, but the contractor went, capped all the holes with some concrete, and then rebuilt the soil profile over top and continued to work on the panel. However, by September, at this point now, there were 11 sinkholes and closed depressions that had appeared in the turf. And everybody agreed that something had to be done because they had to get this project done, and they were constantly going back and trying to deal with all these sinkholes. And so this photograph here you can see is from July of 2016. You can see all the turf is in place, but they're still doing some minor construction around the outside. So we were tasked to figure out what was going on and try to figure out how to solve it. So the first task was to go and look at the available subsurface information. There was plenty of subsurface data available from the planning and design of the mall turf reconstruction project. We also went and looked at the historic data that was available, and the Smithsonian Metro Station, which is a DC subway system. This is the main station, and then this is the running tunnels underground that leave the station. So we looked at that data as well. Then we moved on to an investigation phase. Now, since this was brand new turf that we put down, the National Park Service was not interested in making a mess of it with an invasive investigation. So we focused on a geophysical investigation. We performed GPR, magnetometer, and MASW. So each of these investigations we were hoping would reveal some clues, and each of the methods have different strengths and weaknesses. The GPR system, we were really looking for any buried anomalies that might be impacting it. We were looking for areas that had very wet and saturated soils. And because they had just recently rebuilt the soil profile out there, we were looking for any areas where the soil layers might have sagged. So you could clearly see that something was going on. In the magnetometer, we were looking for the presence of ferrous objects, like more of those steel H-piles that came up in one of the test pits. And then the MASW measures shear wave velocities, which low shear wave velocities are indicative of loose materials. And so you would expect near the ground surface loose materials, but you wouldn't really expect it at depth. So those were the things that we were looking for. So one thing you can see in this photo, we have overlaid the outline of the Smithsonian Metro Station and tunnels over the panel 19. And if you look here on the left in the GPR, you can see the majority of the distress seems to coincide with where the metro station is. If you look at the magnetometer, you can see that there's a remarkable amount of ferrous material right around the metro station. And up here in the MASW, you can see that near the WMATA tunnels and station, there's more loose material at depth. So the takeaway was, hey, almost all this distress seems to be associated with the presence of the metro tunnel and metro station. So you have to ask yourself, the Smithsonian Station was opened for use in 1977. So what's happening 39 years later in 2016 that would suddenly cause the ground around the metro station to become unstable and eroding away? So there were two different hypotheses that were floated out there. One was that the metro station and tunnel were originally formed and not cast up against the temporary supportive excavation. Over 39 years, the wood lagging decomposed, and this left voids, and now soil's washing down into the void. Hypothesis two, if you looked at the soil stratigraphy at the site, it's very well known in Washington, D.C. that there's a layer of cobbles and boulders in the soil at depth. There's a rumor that the metro system, when they excavated for the station as a cut and cover excavation, that they took all these cobbles and boulders and they put them above the tunnel and use them as backfill. And that these boulders and cobbles had nested, creating a network of air pockets. So our geophysical investigation program could not clarify, which of these theories was correct, but they both had something really in common, that the soil profile, the new, more porous, more granular, more draining soil profile with the irrigation system, everything is now possibly washing the soils down into these voids at depth. So the remedial fix had to be able to stop the voids from, fill the voids and stop the materials from washing down. So the National Park Service was super motivated to figure out a solution to this, because the inauguration for the president was only 4 months away. And this was one of the sites that they were planning to use for some of the activities. And they wanted to make sure that they had it in showcase form and ready for use and safe for everybody by the event. So they asked for both short and long-term solutions that would stabilize or repair the situation with as little disturbance to the turf as possible. So we presented for them 4 sort of general scenarios. One is be strictly reactionary. Just anytime a sinkhole shows up, just go fill it in with some soil. And then once the inauguration's over, then you can develop a plan and implement it. Option 2 was to do spot treat grouting. Just treat the sinkhole areas where we know there's a problem. Let's stabilize it. get through the inauguration, and then the National Park Service can think more about what they want to do, and if they want to treat the rest, they can. Option 3 was to go and try to treat the entire perimeter of the WMATA tunnel right away and get it one and done. And then, you know, the final option, we said, like, if you really want to know what's going on and stop it for good, you're going to have to excavate down, figure out what's going on, fill all the voids, and reconstruct. Now, each of these different scenarios had different degrees of disturbance, different durations, different risks, and different costs. One of the things you may wonder is, why did we look at polyurethane grout? So because this project was going to be done immediately next to the metro station, and we were not going to have any way to control where the grout was going, we wanted to make sure that the grout that we were using would not put excessive pressure on the WMATA facilities underground. We also wanted to make sure that the grout would expand quickly, be rigid and lightweight, so we wouldn't have problems with later settlement or breakdown or anything. We did not know how interconnected the voids were underground, so we wanted to make sure that the grout was very high, highly mobile, so it could flow through all different size voids. And it had to be done without driving any heavy vehicles onto the grass. So we laid out all the pros, the cons, the advantages, and the costs to each of these different scenarios to the National Park Service. And they chose option 2, which is spot treat the sinkholes that have already appeared with polyurethane grout. And then, you know, they recognized and they understood that this was not necessarily going to be a one and done, that likely other areas on that same panel could have sinkholes and closed depressions show up later, and they would deal with it at that time. But they wanted to get something done before the inauguration. So because of the inauguration, they imposed some additional requirements on our grouting program. Excuse me. First of all, again, no vehicles, especially heavy ones, were supposed to drive on the turf. The grouting program could not, you know, heave anything or risk breaking or jacking up any of their drainage or irrigation systems, and we couldn't get grout into any of their brand new drainage or irrigation systems. Because there is this known layer of boulders and cobbles down there, we had to make sure that we were able to get the grout down to the depth that we needed to without refusing on these materials. We had to be able to complete all this work before the inauguration and give them time to get everything back, give time to get things set up. And the turf had to be restored back to its original condition. So that was a pretty aggressive thing that we had to try to pull off in a couple of months. So we developed a grouting program, performance specification, and a grouting package that we submitted to contractors to bid on. The grouting package included the requirement that they would have to develop and submit a work plan, that they had to plan for primary, secondary, and tertiary grouting phases to make sure that we really address the problem. Because of this, really known potential for cobbles and boulders, that the primary holes would have to be vacuum excavated to make sure that we were able to get to where we needed to go. And then there were other requirements that we had asked for, like doing upstage grouting, and that we would have to agree on the grout stage termination criteria, and that they would have to perform a test panel to prove to everybody that it would work before we got into the full thing, because we didn't have time to start and then not succeed. So the contract was won by CJ Geo, and we agreed on the ultimate grouting program, that they would vacuum excavate to 10 feet, and then we would grout back up from there, with the goal to try to create a sort of a bridging surface layer of grout and soil. Around the existing sinkholes, we would grout on a primary grid spacing of 5 feet. And then we agreed upon a set of basic grout termination requirements that we all had to watch out for and try to make sure would not happen. So this plan here shows sort of the conceptual layout that we gave the contractor for the test panel. Because the turf was so brand new, a lot of the area in the panel was restricted to not allowing them to enter. So they had a very narrow, limited limit of disturbance area where they could do the grouting. We gave them 2 different locations as options for a test grouting zone. And while they were not allowed to bring any heavy vehicles onto the turf, if they absolutely could not execute the work without bringing something more like a lightweight vehicle or a small UTV or something, but move equipment and move stuff in and out, they were given one narrow access route that was optional, but discouraged. So they did perform the test panel on December 14th. Here's some photos of the grouting underway. First thing they did is the landscape contractor had a specially made steel sod cutter that cut out little squares of sod, and they were preserved for replanting. The holes were vacuum excavated using a water jet and a vacuum truck. Now they use these little segments of PVC pipe as temporary casing in the very granular soils that were used as the original, or as the mall new soils. The contractor decided to use a probe at the bottom of each of the holes to try to probe for voids. That didn't really prove to be too useful, but it was interesting to see. And then at the end of the panel, they demonstrated that they were able to use the urethane foam to properly fill the hole. And part of this was to test. We were looking at 2 different types of foam grout. One is an NCFI 27004 plural component polymer grout. Had very low weights and high flow capabilities. And then also there was what we call mountain grout, which is another low viscosity grout that's more used to fill cracks and voids. So we were testing out, trying to make sure that the sort of reaction time and set times and all that worked before we got really into the full program. So at the results of the test panel, we concluded that the contractor could successfully complete all the work while keeping all vehicles off the grass. So these vehicles were sitting pretty far away, and there were hoses running all across the turf to get to where we need to work. The vacuum excavation program did reveal that there were a lot of large cobbles and small boulders at depth in the soil, but they were successfully able to make holes to 10 feet deep, to 12-inch diameter, sucking up these big cobbles to get down there. The probing revealed that there were no voids, easily detectable. The PVC casing proved to not work for the vacuum excavator. It was just too small and too difficult. So they tried doing the work later without the PVC casing. This was ultimately a very difficult problem. They tried to keep the sidewalls from raveling. The 2-component urethane foam resin worked great from flowability, expansion, set times. The foam, when it was set, while it was rigid enough, it was also easily trimmed to create a nice level surface for the landscape contractors to reconstruct the soil profile on top. So with that successful test panel, production grouting started on December 19th. Unfortunately, the very next day, a big winter snowstorm moved through DC and turned the site into a mess of ice and snow and water for days. This caused a lot of stress to everybody because with the brand new sod on the mall, they didn't want people going and trafficking all over this and creating problems or over compacting everything. So we were on standby or stand down for a while until the site had melted and the water had drained away. But we still managed to get it done. The grouting was performed around all 11 sinkholes. Some locations, there were 6 locations where we vacuumed down, we grouted back up. There were no unusual grout takes. But there were other locations where we had significant grout takes. And when in some of the areas where we had significant grout takes, By the time we were getting through the secondary and into tertiary holes, we realized we were making Swiss cheese of the turf at this point. So we switched over to the single component mountain grout. This was injected using a narrow sleeve, and they didn't vacuum excavate a hole anymore. We were just trying to save the grass. But the vacuum excavation did provide some very interesting insight. There were 4 locations where while we were grouting in one hole and they had excavated another hole somewhere else, we started to see grout cross-communicating between the holes at depth, which clearly indicated that there was some sort of void or conduits down there that was allowing the grout to travel. Let's see if we can get a switch. The most notable or problematic area was at sinkhole 3. So first of all, during the excavation of the original hole, they hit a really large boulder down there that they couldn't bring up. They did an offset hole. They hit the boulder again, still couldn't deal with it. So we switched to the mountain grout, and we injected 9 gallons of unexpended grout into the hole. And there was no resistance. There was no increase in pressure. So people started to panic. Oh my gosh, maybe we're injecting it into the WMATA station or the WMATA tunnel. So we stopped work. We contacted WMATA and asked them to check their facilities. They came back. They said, everything's great. So we went back and resumed grouting in here, and we ended up putting down another almost 50 gallon, a little over 50 gallons of grout between the aviation grout holes and the original sinkhole. And again, still no resistance, no increase in pressure. So at this point, people are starting to get really nervous because we've got 60 gallons of unexpanded grout into this. And for example, the mountain grout has like a 25 times expansion ratio. So this is a lot of grout into a very, very localized area. But we did want to reassure everybody that we really had solidified the problem, that even though we could not get to refusal. So the contractor did a narrow exploratory trench, to use some plywood here to shore it up. The good news is that we did not encounter any unexpected man-made structures. And what was exposed in the hole consisted of a whole heck of a lot of cobbles, boulders, and hardened grout. For additional peace of mind, we still did 2 more grout holes at the bottom of the trench, and those took yet another 50 gallons of grout without resistance. At this point, we had put down 126 gallons of urethane grout into a very, very small area. We had not gotten refusal, but we had reached a peace of mind that even if we hadn't gotten refusal, we had put so much grout into a localized area that, and everything had sort of solidified, that this would bridge over any voids that may exist below, and that it would limit the migration of soils. At this point, we're definitely running out of time, and we felt that we had really done. So at this point, the grouting project was called. So this plan here shows the location of the 11 different sinkholes, as well as the grouting holes that we did around it. Sinkhole number 3, as you can see here, had quite a few grout holes around it, and ones that had, especially the red ones, had very high grout take. In conclusion, for this grouting project, we found that the polyurethane foam grouting was very successful in really sealing up and filling a lot of the voids. The vacuum excavation, while it definitely created more disturbance, it was very helpful for, first of all, getting past a lot of those cobbles, but it also revealed to us the extent at which the voids below ground were cross-communicating. We were able to get it done all together and cleaned up with 16 days to spare before inauguration, which gave the National Park Service time to get everything set up. As expected, this did not solve the larger problem around the metro station. And we understand that additional sinkholes and depressions have gradually developed over time in other parts that are untreated. We do know that CJ Geo was hired by National Park Service the following year to treat some additional locations, and that other depressions as they show up have been simply filled in by the landscaping staff with soil for now. With that, I would like to say a personal thanks to CJ Geo for digging up a lot of the project photos for this after 10 years. And NCFI for all their support with, understanding polyurethanes. And with that, I will just close. This is a photo of that same panel last summer. And you can see that again, there are still in some of the areas that were not treated, there are some new little depressions that are starting to form that will probably eventually have to be treated. With that, I thank you for your time.
Okay, thank you. Thank you very much to all the presenters. Excellent presentations, very informative, and I hope everyone enjoyed them as much as I did. I don't see where we have any questions at this time. If you do have any questions, I would invite you to go through the DFI website. And as it was said on the earlier slide, you can send questions there. Or I would even, and I hope this is okay, but I hope that you could also contact the presenters themselves if you have any questions. I'm sure that they'll be more than happy to take the time to answer anything that you have. I have a few announcements that I'd like to make also. First of all, DFI will be celebrating our 50th anniversary, and we are having our 50th conference. It will be held in Nashville, Tennessee, October 20th to the 23rd. Also, at the beginning of the conference, we will hold a DFI International Grouting Committee meeting, and we generally will set that up not only for people who attend in person, but also remotely. And I'd like to invite everybody on the call, if you're available and if you're interested, either please make it to the conference or call in and sit in on one of our DFI grouting committee meetings. And you're also open to join our committee if you like. We will be holding our next webinar in December. It'll be held on December 2nd. It'll be at the same time, 11 to 12:30 Eastern Standard Time. We are working on a subject matter that I can't really disclose right now, but because it's not locked in. But we will be putting out announcements later in the year as we know for sure that we do have our presentation theme that will be going on for our webinar, and we'll be putting information out for that shortly. So thank you everyone for attending. We appreciate your attention and we appreciate your taking time out of your busy schedules to join us. And with that, again, I'd like to thank all of the presenters. We appreciate your time. Thank you.
Thank you.
Thank you, everyone.
Thanks a lot, guys.